Hello everyone, welcome back to the NPTEL course on materials informatics. In today's session we will continue our discussions on neural networks. Just to recap, in the last lecture we looked at how perceptrons were first sort of formulated in the 1950s and the problems associated with simple perceptrons, in that they are linear models. And then you had to stack the perceptrons to create multi-layer perceptrons, which are the sort of origins of modern day artificial neural networks. And of course artificial neural networks by construction have a few problems in the sense of how do you initialize weights, how do you train weights, and that is where initialization schemes were sort of invented, and also backpropagation as an algorithm was used to solve many of these mathematical problems, alongside good activation functions as well. So a combination of these have made neural networks quite powerful and quite useful in the modern era. And we also looked at a few general guidelines, and we basically stopped at this point here where we said that there are a couple of different ways by which you can build neural networks using Python. One is the Keras package, which also has an API, so it sort of works with what is referred to as TensorFlow here, which is also a package here. This is a more recent package. The documentation is quite good, and the syntax is also fairly simple to build neural networks. But in the case of sort of codes and packages related to material science, most of those packages have been written in PyTorch. Largely because PyTorch is more versatile, it is more modular a code compared to Keras, and also for legacy reasons. So it's a good exercise to look at how to build neural networks both with Keras and as well with PyTorch, and that is what we will be doing in today's session. So we will first look at how to build neural networks using Keras, and then we will then look at how to build them using PyTorch. So just to give an example of how the syntax looks like, and then we will go to the Jupyter notebook. So Keras is basically a module from this TensorFlow package. So you import Keras first, and then you have to sort of declare the model architecture or sort of initialize the model architecture. So we basically say that it's a sequential MLP, or a simple what we refer to as feed forward neural network. And then so this is a simple neural network, where all the connections are where we want to connect all the nodes to the other nodes in the previous layer as well as in the next layer, right? So that's what we have in mind here. And let's say we want to sort of construct this neural network architecture for a classification task, a multi-class classification task, right? So the way we would do it is, the first is we have to declare what is the how does the input layer look like. So we are going to use a data set that is similar to MNIST, but it is called a fashion MNIST data set. I will explain what is the data set shortly when we go to the notebook. But the data set pretty much looks like MNIST itself. So it is a 28 by 28 pixel data set. So our input layer, or the set of input nodes is basically going to be a flattened version of this 28 by 28. So basically it is going to have 784 nodes, right? So that is the first layer. So the first layer basically refers to the input layer which has been added to this sequential neural network model. The second one is a dense hidden layer, right, and it has about 300 nodes, and it is going to use an activation function of ReLU, right. So this is a hidden layer, and we only have one hidden layer here. The second and the final layer is basically your output layer. It is also a dense layer. It is basically connected to all the 300 nodes here. It itself has 10 nodes, so there are 10 different classes that we can assign to our to any possible outputs. And since it is a multi-class classification, so we are going to use this softmax activation function, right. So this is how the model is declared. So we have an input layer, we have one hidden layer, and then we have an output layer. And in Keras, whenever you declare a model, you also have to compile the model. So this is an additional step compared to classical machine learning models, where you don't really have to compile them. You can create an instance and then directly fit them. But this compile step is important, and we can also pass in some hyperparameters in this compile step. So we can sort of define our loss function here, we can define what kind of optimizer we are going to use. We just say that we are going to use stochastic gradient descent. It's a simple enough neural network architecture. So we will use one of the simpler algorithms here, not ADAM, right. And then what kind of metrics are we going to track. So we are going to track accuracy as a classification metric, right. So the model itself will minimize its cross entropy. So cross entropy is the loss that it will try to minimize, but we are going to track an additional parameter which is accuracy. So you can also put in precision, recall and whatnot here, right. So that is in the compile step. So compile step gives you a chance to put in a few other additional hyperparameters, right. So once you have compiled your model, you can then fit your model. So when you fit it, you have to pass in the train data. So x is the set of features, y is the set of targets, how many epochs do you want to actually train the model. So this is a number again that has to be tuned, but we will take 30 as as a starter. And then this validation data is an optional argument, but it is highly recommended. So you can give it a validation set as well to examine how the model is varying in terms of its performance, like its loss value, how is it varying with respect to validation data. So we can also pass in a few validation data points here, both in terms of features and targets, right. So once we have fit the model and once we have sort of identified an optimal model, you can then use that to do production runs or make predictions, right. And that function is again similar to what we have used before in classical models. So we just use a predict function here. We can also do what is referred to as an evaluation. So evaluation basically tries to understand whether so in the case of prediction, you simply output a predicted value. In the case of evaluation, you can also evaluate the kind of loss that you have on your test set. So if you already know the target y values, the target variables in your test set, you can then evaluate how the model is performing on your test set. So evaluate is one other additional function that you commonly encounter in sort of neural network architectures, right. So just as a summary, right. So we first have to declare what type of model we want to create. So we are creating a simple what is referred to as a sequential neural network model. We sort of define how the model is constructed, so how many layers, how many nodes per layer, what type of activation functions and so on. We then compile the model, specify a few additional hyperparameters such as the loss function, what metrics you want to track, the optimizer, and then we fit it. So the compile is a new step compared to classical machine learning models. Fit and predict are typically how you would use in our in the classical models as well. The only difference being that in fit you can also pass in some amount of validation data here, and then you also have an evaluation mode to evaluate the model directly on a test set, right. So let's now get to the notebook and let's see how this is actually implemented in practice. So just as a starter, right. So we have to of course set up several things in our Jupyter notebook. So that's the first cell here in this Jupyter notebook. So we are importing some amount of scikit-learn, I mean because it has some useful modules that we can use. So we are going to import scikit-learn, then TensorFlow of course, and then NumPy because it's quite useful. And then we basically declare how we want our figures to look like. So simple labels, tick values and so on, and then where we want to store whatever images we are going to generate in this work. So that's what we are going to put here, and then we also define a save figure function just to save figures on the fly, right. So the first block is nothing fancy, it's just declaring and importing necessary things, right. So our objective is to build an image classifier, and it is a classification of the fashion MNIST dataset. So in the MNIST dataset we had a bunch of images and we had numbers associated with each image, right. In fashion MNIST we just have costumes or things that we wear on ourselves as the possible set of items, right. So in MNIST we had numbers ranging from 0 to 10, here we could have shoes, we could have jackets, we could have shirts, pants and so on, right. So different fashion items and the compilation of those fashion items is our fashion MNIST dataset. So we are going to use this fashion MNIST dataset. It's a very simple to use, simple to evaluate dataset. datasets. It's slightly more complicated than the regular MNIST dataset, so that's why it sort of makes sense to try out neural network architectures on the Fashion MNIST dataset. Okay, so while building an image classifier, so first thing we have to do is import Keras, the Keras module. We just check whatever versions of TensorFlow and Keras we have imported. So the recommendation is about 2.15 or above, and then Keras version of 3.8 or above. I think these sort of work well with this notebook. So if you want to try these notebooks by yourself, ensure that you have installed the TensorFlow and Keras dependencies correctly. Those can be installed fairly easily, so just Google up how to install TensorFlow and then just follow the instructions and it should work out. Right. Okay, so the first step is to basically obtain the Fashion MNIST dataset, and luckily, so just like scikit-learn had its own version of the regular MNIST dataset, Keras has its own version of Fashion MNIST dataset as well. So we can simply sort of download the dataset from Keras itself, and that's what we have done here. And the dataset itself contains both the training component, the train split and the test split, right. So we don't have to explicitly split the dataset into training and test, right. So this is just like how scikit-learn sort of categorizes the MNIST dataset as well, right. So there the dataset is fully random and it's very easy to create a train test split. Here the train test split is automatically generated. So as long as you load the data properly, you will already get your training features and your training targets and your test features and your test targets. Okay, so the training dataset basically has about 60,000 grayscale images. So again, once again very similar to your MNIST dataset. Each image is a 28 by 28 pixel and it's all grayscale images, right. So basically black and white color. The test set has about 10,000 data points. So we can check how the train and the test set look like. So sorry, how the train data set looks like. So it has 60,000 data points, each 28 by 28 pixels. And in terms of the type of the data, it's all integer data. So if it's either 1 or 0 depending on whether the pixel is it's all integer data. So each pixel has a value between 0 to 255 depending on it's the amount of gray that it has. So it has one integer per pixel basically. Okay, so now that we have the train dataset, let's now split the train dataset into train and validation. That's one aspect. The second aspect is we want to normalize our features, right. So our features go from 0 to 255. That's not a very intuitive scale for us and for machine learning models. So we might as well just divide by 255. So that gives us a distribution from 0 to 1. So 0 being the lowest value and 1 being the highest value in any pixel, right. And that's what we do here. So first is we sort of create a train validation split here. So the validation set is going to be the first 5,000 data points of our training set, and the rest is basically going to be our training set itself. So the 60,000 data points, we split that into 5,000 validation and 55,000 train. And this data set, when you load it, is fully jumbled, it's fully random. So you can take the first 5,000 data points without worrying about random sampling, right. So it's the same thing we do for the y values as well, right. And then the last line here basically ensures that the features of your test data set are also normalized. So they are also normalized by 255, right. So we just divide each sort of each item in the array by 255 here. Okay, so just to give a sense of how any given data point looks like, so we can plot them using this imshow function within matplotlib like we have used before, and if you plot it, you see that it's this is a sort of a pixelated image of a jacket, right. And if you want to see what kind of y values we have correspondingly, so all the target values are all numbers. So they are basically ranging from 0 all the way to 9, right. So it's actually useful for us, right, to actually track these numbers well. So we can assign a set of class names, and once again these class names are based on how the data set itself is defined. So we just need to look up the documentation to see what 0 corresponds to, what 1 corresponds to, and so on. So 0 in this case corresponds to a t-shirt, 1 corresponds to a trouser, and for example a pullover is a pullover which is also equivalent to a jacket is basically 2, right. So we have defined our class names. So if we now okay, so it looks like the image that we loaded is classified as a quote basically. So if you actually so we sort of visualize the first data point in the training set here, which I said is a jacket. So it's basically it's considered a quote in the data set itself. So once we assign a class name for our target value, we see that the target value is actually 4 here. It has an value of 4. So 0 is t-shirt, 1 is trouser, 2 is pullover, 3 is dress, and 4 is coat. So it's basically a quote, right. And we do see that the target class name is basically quote, right. Okay. Now just to check that the validation and the test sets look okay. So we see that the validation set has about 5,000 data points and the test set has about 10,000 data points, right. Okay. Let's now try to visualize several images in a sort of a matrix kind of form. So just a simple function here that does the same. So it should create a 10 by 4, so it will basically visualize about 40 images, and you see all the different types, right. So you see coat that we visualized before, t-shirt, sneaker, ankle boot, dress, pullover, and so on, right. So there are basically 10 different types of fashion items that are being stored in this data set, and our job is to classify these 10 items. So it's a multi-class classification task. Okay. Now let's get to the real business end. So first is we sort of ensure that we sort of clear any session variables that we may have declared. So if you use the same notebook multiple times, the kinds of models that you may get may be different. So it's always better to, whenever you use Keras, to always clear out whatever session variables have been declared in your Jupyter notebook, so that you know that the fit is correct, right. And we also define some kind of random seeds here to ensure reproducibility, and then we declare our sort of neural network model here. You can sort of ignore the warning message. So I have used the same syntax that I presented in the slides here. So I first declare a sequential model. The first input layer is basically a 28 by 28 node input layer, so 784 features. The only difference is that the number of hidden layers is actually 2. So the first hidden layer has 300 nodes, the second hidden layer has 100 nodes, and the final output layer has 10 nodes. So 10 possible classifications or 10 possible classes that you can assign, that you can assign to one of your data points, right. So for the hidden layers, the activation function is ReLU, and for the final output layer, the activation function is softmax. So out of the 10 classes, only one class will be assigned to whatever data point you feed your model. Okay. So once you sort of initialize a model, you can actually get more information about the model itself by using this model.layers attribute. So if you do that, you see that it says, okay, the first layer is a flattened layer. So flattened just means it's an input layer. So it basically takes the 28 by 28 matrix and then creates a vector, right, one single vector, and then the second or the two middle layers are basically dense layers, hidden layers, and the final layer is also a dense layer, but it's an output layer, right. You can also use this model summary function, which is a very nice function. It also tells you how many parameters you have in your model. So for example, in the first layer you don't have any parameters, that's just your input layer. So you take all the zeros and ones, or values between 0 to 1, because we have normalized all the input variables here. So it will basically be one floating point value, right. So that does not have any sort of trainable parameters, the input layer. The first dense layer has sort of 300 nodes, and it has 235,500 trainable parameters, right. So what do I mean by or how do we ensure that there are 235,500 parameters. So it's basically the way to calculate the number of parameters is, if you have a dense neural network, each node is connected to every other node in its previous layer and in its subsequent layer also, but in its previous layer it's connected to every other node, right, and for each connection it will have a unique weight, right. So here you have 300 nodes that are connected to 784 nodes in the input layer, right. So there are basically 300 times 784 weights that you have for that hidden layer, right. To train one hidden layer you have 784 times 300 weight terms, right. So that should give rise to about 235,200 parameters, and the remaining 300 parameters are basically your bias terms. So each of your nodes in your hidden layer basically has a bias term associated with it. So each node has 784 weights for each of its connections to the previous layer, and it has its own bias term, right. So there are 300 nodes and hence 300 bias terms. So if you add them up, you will basically get 235,500 parameters that you have in your model, that you can train in your model, right. So you can do a similar math for the second hidden layer also. So this has about 100 nodes, the previous layer has 300 nodes, so it's 300 times 100, so 30,000 weights that you have plus 100 bias terms that you have, right. So that's why the number of parameters is 30,100, and the final layer, the output layer, again it's a dense layer, right. So it's going to have 10 times 100, so that's 1000 weights and then 10 bias terms, right. So each of your each of your nodes in your output layer is going to give you an output which is going to go through a softmax function, right, and then you will get one single value. So one single value corresponding to your target, somewhere between 0 all the way to 9, right, and 0 means one type of image, 1 means one type of image, and so on, right. So that's why if you do a model.summary, you can get a very nice summary of how your neural network is structured and how many parameters you have, right. So in general, neural networks, the parameters will explode quite quickly. So it is that's why these architectures can overfit very easily, right. So if you only use 100 data points, right, to fit this neural network which has about 260,000 260,000 trainable parameters, then it is very likely that the neural network will actually overfit, right. So you either have to increase the number of data points or you have to have very strong regularization methods, right, being built in. So the number of parameters is about 260,000 here, as you can see. In neural network architectures, depending on how you construct them, you can also have some parameters that are trainable and some parameters that are calculated by the network itself. So it's not really trainable, it's dependent on how the values of the other parameters, right. So those parameters are what are classified as non-trainable parameters. We won't worry about it now because we are dealing with simple sort of dense feed-forward neural networks. Okay. So once we have done that, let's so you can also visualize how this neural network is actually structured. So you can create these simple node and followed by sort of edges indicating how the nodes are connected and so on, classic neural network images. You can use this line of code to generate those images, but of course you will need an additional package. So that's why you need this package called GraphViz. So if you have that GraphViz, then this line of code will work and you can actually generate a nice image of your neural network. Okay. You can also check how the hidden layers are named. So for example, the first hidden layer is named as dense, the second layer is named as dense_1, right. And then it also says, okay, if this is just to check that if the layer itself is hidden, and it says yeah, it is hidden. You can get the sort of weights that have been initialized. So when you initialize the model, it will automatically initialize some weights using one of the initialization schemes. So you see that the weights have been randomly assigned. You can also check the shape of the weights. So you see that there are 784 input nodes times 300 weights, right. So that's why this is the shape of the weights. you can also check the biases. So all the bias terms are 0 initially, but they will be learned in the future. So once your model has been trained, if you want to recover back your weights and biases, you can basically use these commands, right. So as of now, since we have not trained the model, it is giving out a random set of weights and biases, right. So we have declared we have created an instance of the model, and we have also looked at how the model is structured, and we are happy with the model. Now it's our job to compile the model and make it ready for fitting, right. So as I mentioned before, so we are going to compile the model using categorical cross entropy as the loss function. We are going to use stochastic gradient descent, simple algorithm, and we are going to track accuracy as a metric, right. And there are a couple of different ways that you can sort of declare this in your code. So you can either use loss equals, for example, loss equals sparse categorical cross entropy under quotes, or you can also use one of the attributes within Keras itself. So Keras as a losses module or a losses class, I think, and then within that class you have sparse categorical cross entropy attribute, which basically gives you or calculates the same cross entropy loss, right. So there are a couple of different ways that you can declare, you can compile your model. So I have just given you examples of both syntaxes. Okay, so now it's our job to actually fit the model. So let's start fitting it. This may take a few minutes to actually run. So let me execute the other cells as well as I explain. Okay, I'll go all the way to evaluation. Yeah. So basically when you do a model fit, you see that we have declared that the model has to run for about 30 epochs. So for each epoch it has about 1700 iterations. So it has split the training data set, which has about 55,000 data points or so, to roughly about batches of 3 or so, batches of 30 or so, and hence you have about 1700 sort of iterations. 1700 steps in one epoch, right. So when the model completes the sweep over 1719 iterations, it basically has seen all the 55,000 data points in your training set, and it has completed one epoch, and we have asked the model to train for about 30 epochs, right. So and it also prints a lot of terms here, right. So for example, after the first epoch, Keras basically tells you that the model took about 5 milliseconds per step. So the total amount of time that it took for one epoch is 1700 times 5, so that means 8.5 seconds, right. So it takes about 5 milliseconds per step, and we said that we asked the model to track accuracy as a metric. So it's printing out accuracy and the loss, which is the cross entropy loss in the training set, and it also does the same for the validation set, because we have passed in a validation set within our model fit. Where is model fit? Yeah. So we have also passed the validation data here. So and hence the model when it's fitting, it will also print out the validation accuracy and the validation loss, right. And it's almost always a useful exercise to store this whole fitting process into a history kind of variable. I mean, you can call it history or any other variable, basically because it makes us it makes it easy for us to analyze and understand how the model is actually fitted, and declaring that in a variable also helps us visualize how the loss is evolving, and sometimes also helps us choose the right or the most optimal model. So let's say you are using early stopping as a regularization criterion, then you have to identify which model is good, right. So for doing all that, declaring a variable associated with your model fitting process is often useful. Okay, so we are running about 22,000 steps. So soon enough, few more seconds. So I'll just explain the other cells as well, and they should get executed fairly soon. So the history parameters basically tells what are the parameters that the history variable is storing, what it has seen during the fitting of the model, and then we'll sort of print out a few things, right, of what the history variable is storing. And then the other nice thing is once you have stored your fitting process as a history variable, you can then convert that variable into a standard pandas data frame, and then use all the input inbuilt pandas functions to do visualizations, to calculate metrics and so on. Okay, so we are at the 28th epoch, 2 more and we are done. So you see that roughly each epoch is taking about 8 seconds. So this epoch took longer at about 10 seconds. Yeah, so we have entered the last epoch here. Yeah, so you see that history parameters basically tells you, okay, so the number of epochs was 30 and the number of steps per epoch is about 1700. So it also tells you how many epochs it has seen, right, and what kind of values it actually stores. So it stores accuracy loss, validation accuracy and validation loss. We can then convert that into a standard data frame here, and basically we are plotting the training accuracy and training loss as well as validation accuracy and validation loss. So in general you expect the accuracy terms to increase and the loss terms to decrease with increasing training, right. And you see that the validation loss is sort of tapering still, it's not reached its minimum yet. So we could take the last available model as the best model that we have so far. And we can now do an evaluation. So when we do an evaluation we basically see what is the accuracy with respect to our test data set, which is about 5000 data points here, the test data set has about 10,000 data points. So the model runs or makes a set of predictions on the test data set, so 10,000 predictions, and then it evaluates against the 10,000 target values, which is in the y-test variable here. So it has an accuracy of about 0.87. I think this is similar to the accuracy on the validation set, right. So it's not too bad, the model is performing decently well. I think training accuracy you almost always expect to be larger because the model is actually seeing the training data points. So it is exhibiting a decent accuracy, so that's good, and the loss is slightly on the higher side compared to validation loss, but this is not too bad. It's not a terrible fit. I mean, for a first fit of a classification model using neural networks, this is not terrible, right. We can now ask the neural network model to make specific predictions. Let's get to here. So let's ask the model to make a specific prediction on a specific data point. So this is basically the first 3 data points here, and these are the kinds of outputs that the model is giving, right. So you have 10 different classes, right. Out of the 10 different classes, the probabilities are 0.03 for this class and 0.96 for the last class. So of course the softmax function is going to choose the maximum probability. So the first for the first data point it's basically going to assign a value of 9, second data point is going to assign a value of 2, and this is going to be a value of 1, right. And this is what we are going to see, 9, 2 and 1 here. And what is the so according to the classes it's basically an ankle boot, pullover and trouser. Those are the first 3 data points in the test set, right. Let's see what the actual targets are. The actual targets are actually 9, 2 and 1. So the model has actually accurately classified them, and if you want to visualize them, so this is the ankle boot, pullover and trouser. Those are the first 3 data points in the test set, right. So it looks like the model has actually worked fairly well, and it is able to do multi-class classification as well. Alright, so let's now look at a simple regression example as well using our multi-layer perceptron or artificial neural network, and we are going to once again look at the California housing data set. So where we wanted to predict the median house price, right. So once again let's do the basics. So we will fetch the data set, we are going to split that into train, test data sets and so on. We will initialize random seed. We then declare the model. So as the model is training, let me explain what we are doing here. So we are doing a regression task here. So once again we are creating a simple neural network model. We only have one sort of dense layer as a hidden layer here, which has an activation function of ReLU, and it has about 30 nodes. And this is a slightly different way of declaring declaring our input layer here. So you can either have a separate line that says model add add layers and then flatten, or you can just add input as an argument to your first hidden layer, right. So basically what it does is it tells the model what is the shape of the inputs and how many nodes your input layer should have. So your input layer will have the extrained data set here which has been flattened out, and this is the first hidden layer which has an activation function of ReLU, and it has 30 nodes. The output and we only have one hidden layer, subsequent to that is just the output layer, and there is only one output node. So we want to predict the median house prices, which is one floating point value. So we just have a value of 1 here, and there are no activation functions in the output, because in regression models we typically do not need activation functions unless we really need to create some kind of bounded predictions. So we want the minimum value that our model predicts to be a certain number, the maximum value to be a certain number, right. So and then we compile the model. The loss that we are going to track is mean squared error. We do not really need any other metrics to track. And the optimizer is once again our stochastic gradient descent, again a simple optimizer, and we are going to use a learning rate of 1 e to the power -3. This is again a hyperparameter, right. And then we do a fit. We are only training the model for about 20 epochs, so not a lot of training here, and then we also do some evaluations, right. So we evaluate on the test set, and then we see what the predictions are for the first 3 data points in the test set, right. So the model has done the training now. So the first 20 data points are the first 20 rows are basically for the training, so it has taken 20 epochs, and then the final figures here, so this is basically the loss for your tests, for your evaluation on the test set, and I think one on one this is basically your predictions. So what the model is actually making predictions for the first three data points of your test set here, right. So the one out of 1 is basically, this is the prediction step that we have called here, right, and this is basically evaluation on your test set, and the first 20 rows are basically the training on your training set. The loss here basically refers to your mean squared error, right. So that is the loss metric that we ask the model to minimize it on, okay. So we can now see how the loss is varying. So if I am not wrong, the blue is the validation loss, the orange is the training loss. So the model has not hit its minimum value in validation yet, so it will probably still become better. And let us see what the model is predicting in terms of the first 3 data points in the training set. So we ask the model to make some predictions here. So we are basically listing the predictions here. So it is giving out 3 values, so 0.67, 1.69 and 3.37, and let us see what the actual values are. Actual is a 0.47, 0.458, 5, right. So the model is not particularly great. I think that is probably expected. It is a very simple model, not a lot of parameters, and we haven't done any hyperparameter tuning as well. So so this is okay for starters. This is okay, but the model can certainly be improved. Now let us look at 2 other quick aspects before we close this session. So one is how do you save the model and how do you restore models. So let us say you are fitting a model, and you probably saw in the classification task each epoch is taking about 8 to 10 seconds, right, for fitting. So let us say you give here we only tried out 30 epochs, but let us say you give 300 epochs or 3000 epochs for your training. Then you are going to spend a lot of time training your model. So if you have any interruptions during training, or if you have any sort of data loss during training, or if you want to stop, let us say you have limited resources or limited time, you want to do training for a certain number of epochs, stop it, and then take the model from that point and then train it further, right. If you want to do stop start kind of training, then you need to certainly find a way to save the model, either at at the end of your training or at periodic intervals during your training, and you should be able to find a way to restore your model. So if you have saved the model, you should also be able to restore your model so that you can continue training, continue evaluations with the model, right. So this code block here gives you examples of how to do that with Keras, right. So once again we will declare some random seeds. This is we are going to stick with our regression example. So California data set here. Here the model is slightly more complicated. So you see that there are 2 hidden layers now, each having 30 nodes, dense hidden layers with an activation function of ReLU, and then you have an output layer, and then the input layer is just your set of input features, right, that have been flattened out. And then we once again do compilation and we do fit. So we are only training for 10 epochs here, so this should be fairly quick. And then we also evaluate the model on the test set, right. Okay, so we see that if you look at the validation losses are decreasing all the way. So probably the last model is the best model. So I can save my last possible model by just using this model.save, right. And once I save that, my model will be saved, so it will be written into a file in the directory that you have mentioned, or in the current working directory that you have. And if you want to load that model, so you have saved the model as my_model.keras, that's the file name here. If you want to load that model back and do some more evaluations or do some more training, you just use this load model function, and then you declare that into a model variable or whatever variable that you want to have, right. Now once you have loaded the model, you can use it to make predictions. So you see that XNew is basically the first three data points here, and it is trying to make the predictions on the first 3 data points of the data set, which should be the same ones as these ones here that we looked at before. And you see that the predictions have become somewhat better, or not really better, they're still quite bad, right. And if you want to save the weights of your best model, you can also do so. The typical extension that you use for saving weights is this H5 extension. So you can use that to save your weights, and you can also use load weights function to load your weights, right. So if you let's say you want to create a fresh architecture, but you want to use an existing set of weights to initialize some of the weights of your fresh architecture, you can use these load weights functions and so on. Right. The final thing that we look at is what is referred to as callbacks, right. So we saw that during training, especially if you want to use early stopping as a criterion, right, your validation losses will decrease, and then it may hit a minimum, and then it will increase again. So that's how early stopping typically works, and the most optimal model is the model that has the lowest validation loss, right. So in order to identify that model and save that best possible model that we have, we can use what is referred to as a callback feature, and this is also an inbuilt feature in Keras, makes our our coding process that much more easy, right. So in order to use this callbacks feature, so let's once again declare, we will use the same regression example, so same model architecture, so it's 2 hidden layers, 30 nodes each, and we are going to compile and fit the model. So the key aspect to note is you have to define a checkpoint variable which basically uses this callbacks feature, and it basically tells which model to save, right. So the checkpoint variable will basically save the best model, so the model with the lowest amount of validation loss, right. And then you can once again fit the model. So in the fit function itself, you along with the validation data, you also pass in the checkpoint variable that you or checkpoint instance that you declared before as a argument for your callbacks variable here, right. So once you define this and you start fitting your model, automatically the model will load the best possible model in your my_model_cb.keras file here. So _cb.keras is the file name that you mentioned here. So basically the checkpoint file will save the best model, model with the lowest validation loss in this Keras file here, right. So once you pass that into your fit function, your model is automatically stored in this file here in your current working directory. So you can use the load model function to basically retrieve it, to retrieve it and load it. You can train it further or do evaluations, right. And basically what we did is we reloaded the best possible model, and then we did an evaluation on the test data set here, right. I think the best possible model should still be the last model, according to this training. So the last validation, so the validation loss for the last epoch is still the lowest of the lot. But if you increase the number of epochs, so let's say you increase it to 100 or 200, you may see that the validation loss sort of hits a minimum and then it sort of increases back. So in which case, if you use this callbacks feature, your callbacks feature will store the model with the lowest validation loss, which is how we use early stopping as a regularization feature, right. So there is a lot of new and innovative things that can be tried out with Keras, with artificial neural networks. There are a lot of different rooms, different flexibilities available. So you can always use these notebooks to play around and enhance your learning, right. So with that we will stop this session. We are not completely done yet. So we looked at how to construct your neural network models using Keras, but in the next follow up session to this we will look at how to construct neural network models using PyTorch, right. So with that I thank you all for joining. I will see you all in the next one.